Again, for being here bright and early for students, especially grad students. Who is grad here? Wow, that's discipline, right? So on the video, the undergrads, because we know in terms of the sign up, it's half and half. Anyway, so all the undergrads that are watching from the video, you're underrepresented here. So I hope to see you sometime. Okay, I mentioned about the World Trade Center, and just to make sure that I keep track with my promise to give you some examples, I decided to bring it in. It's only going to take a few minutes, and then we'll move into casting. And I promise you, what I want to do with casting is make it interesting and something that you'll remember some pieces. I've taken a full semester classes or more on casting, and I did enjoy it, but I understand it's not necessarily everybody that needs to know all the details. We'll try to cover a lot of things that, as any engineer, if you know that a casting is just very different, both in terms of corrosion resistance and mechanical resistance than a rod product, you already have a good head start to some of the other mechanical engineers. So we're not going to set the bar too high, but it is, you know, a graduate course. I'm going to try to go through some details. So again, this example here, what I want to do is emphasize how, we mentioned something on the first class. I said, if you're trying to design something for the first time, good luck to you. You know, if you don't take into account everything that other people have done in the past. And that's why when there's failures that are unusual, there's a lot of value in going to learn what happened. You will hear sometime in the class some failure analysis work that is related to deciding who is going to pay. That's called litigation. But the underlying aspect of what there is to learn and improve on is very, very important. So World Trade Center, you know, very, very big tower. Who's been there before? I'm older generation, so I've been there twice before. You did, okay. So it was 110 stories or so with a very, very nice view on top. Very modern building, built relatively efficiently. In New York, they're able to sit on the actual rock. So they go deep enough, so it's very sound structurally, and they can build tall without having all these surrounding base structure. The idea of any construction that is big is you need to meet the code and make it as affordable as you can to the people that are sponsoring this, because it's very, very, very expensive. It does boil down to sometimes being boring for a structural engineer, because he's not asked to make something pretty or super duty. He is asked to meet the code. So the importance of the building code is tremendous. What they did to the building code as a follow-up from 9/11 is a very significant improvement on how you design and implement fire protection. So on 9/11, there's you know, all the fuel from the plane that was eating up these joists that made the floor. So these are joists, they have concrete on it. We don't see the concrete, but you can see it bow. So what happens is you have the two vertical columns on each side of the building, and then what used to be your floor, so a joist right here with all the webbing that you need for structural efficiency, it became more like a rope with a lot of hanging weight pulling on each side. So you can see over time it started to pull on the column, and there'll be a couple of images. This one, I can't say we see it super well, but let's keep going. You see it here. So if you draw a straight line, you see there's at least one floor that caved in a lot before anything else happened, anything else. So when people will come and say, well, you know, melted the steel became really, really soft. You know, it's the true story is a little bit more specific. And there's so many ways that you can do and avoid this and delay by hours and hours, if not completely eliminate the collapse, if, for example, these connections just pull out and the floor goes down one floor. It's not great, but it's very different than the entire tower collapsing. So that was one alternative that they thought of. And the other alternative is, yeah, I mean, don't use the structural steel there if you can avoid it. It's very a thin wall, metal frame that can be subject to heat or insulated. So you have 2 or 3 options. And what it boils down to for a high-rise building like the Liberty Tower that replaced it is really thinking about what happened. If you have a lot of heat, it's going to happen again. You know, we don't know when, but it will happen again. And there are ways around it that are practical. It's engineering. It's not discovering a completely new physics or anything like that. It's not necessarily adding tremendous costs. It is forcing you to think, what am I going to do if this happened? The releasing of the joist, I believe, was really one of the things the engineer thought was a great idea, but you know, there may be some other people that disagree, because then you need some more redundancy. You still need a frame to hold the building, and you have to insulate those in that case. So the reason for using steel, and you'll see that, I'm sure, with Professor Eager, is the toughness. It is able to give before it breaks. So you need steel in that building, or some form of reinforcement, some form of toughness, so it doesn't all collapse if you have a seismic event. But that same steel, the softening of it and this pulling action is kind of what seems to be the consensus. That took a while, though. It took years for people to start agreeing and reviewing those images. So I cover a lot more failure analysis in the spring, but one aspect that I always bring up is look at everything you've got. You know, you can go and think in your head, oh, I think this is what happened, or I think this is it, but the actual detailed photos here is what happened. So it caved in. How can you explain it? And to me, that does explain it. So it is a big exercise. I think it's easy to do a failure analysis and miss something, to tell you the truth. So my only suggestion there, if you have a broken piece or anything that you're trying to know why it didn't work, is try to see all the information you have. And of course, there's some that's not going to help you, but you're supposed to be able to explain, like whatever theory you got should be explaining those photos. Otherwise, you're still, I guess, on an earlier stage. So I hope it helps you when we go real fast through some examples and just point out, oh, you know, here they forgot this, here they forgot that. There's just a lot of value in going backwards sometimes. Even any flooding, the event in Louisiana back a while ago, the flooding from Hurricane Katrina, there's just so much to learn on those levee, on the code, the safety requirements. It's not the number, it's how you use it. You know, if you say, I'm going to make this 30% stronger than it needs to, all right, 30 sounds a little low. You know, it's not a huge margin, but I guess it depends what you consider your worst case scenario, and then you can work from there. There's something that I discussed also in the spring is in terms of just an airframe, the landing gear of an aircraft. If you talk to the aircraft engineer, he's going to come and tell you that he's got a 15% safety margin on that, as opposed to a factor of 2 that we design for a building. Traditionally, now there are new ways to design the buildings that shave this down. But traditionally, it will look like you have more safety on the building, but it's because you don't do the same calculation. If you design the landing, you do take the worst case scenario. You have all these readings from people landing in hard conditions, and you use that worst case load that you know about, and then you take your worst case material property that you know very, very well, because this material has been used thousands of times, exactly made the same way, and then when you combine the two, you can have a very small overlap, essentially, a small spacing between, you know, strong enough, the demand and capacity, what we were talking about. So these are very kind of I call them engineering. You can call them anything you want, but it's just more, the more you know, the more you can, pencil it down more refined and have more efficiency of the use. It's not required for all the cases. If you're going to make one prototype, you just overdo it, right? So you're not going to have a problem. That's what we do with our tester. A lot of stuff we never really even drawn and try to calculate loads. We just figured if we use this size bolt, it's going to be good enough, So, and that's okay. It's really when you come and make quantities. And that ties in well with today, actually, because when you're at the point of making castings, a lot of time you're starting to be in an optimization. And I'll qualify a few exceptions. So in course 3, we had a project for Tiffany, the jewelry people, where the platinum rings for engagement they make, relatively famous and all that. And one thing you don't want is these things to be loose or find out that there was a problem with it if you paid top dollar. So that, for them, quality is very, very important. And they can make them very, very custom, and we'll go to exactly how to do that. So I guess it is one example where it is still a very, very small quantity. They can make unique rings through castings, but in general, for a structural application, let's say I got this chair, the first one I built, I'm not going to cast any components because that requires putting together a mold and a lot of processes. I'd rather just take raw material and assemble it together. So typically, we are looking, if it's just a structural application, we are looking at high volume. So I'm going to give a few examples. We're going to talk about how we actually cast metals and what's involved when that happens. So this is a really typical example. A lot of fittings used for plumbing are cast. And the reason is here you're looking at a complex geometry. It's empty internally. So if you're going to try to take a piece of steel and make a valve like this, you got a big hole to make and a lot of other features that are really, really hard. So if you are okay to live with the reduced mechanical strength, then you go ahead and make a casting. Now, I do want to point a few things. The first one is, see these lines here. This is something that was machined, and we talked about this last week. Here they machined for the bearing. So it's not because you cast that's the final operation. So it's relatively common that there's going to be a follow-up operation, in this case to get these flanges really nice looking. Sometimes if it's just a more simple piece of plumbing, they have to put threads. So they machine the threads, and that's how they get a really good fit. I didn't bring the threaded component. But so we do that because it's less energy, it's less costly than trying to start from a raw material that you work into this shape. If you could make this out of a forging, I circulated one last time, relatively complex, but there's so many operation of pressing in different direction to get there that's not worth it. Now, what happens? Why am I saying, be careful with mechanical properties? It has to do with how the metal solidify. And the example I gave last week was just ice formation on a glass window, that it starts at one spot and then you have different looking crystals, really. These are water crystals going in different directions. So you have the same with metal, and that may not be the best example. We have better examples later. But the idea is, if you take something liquid, and when you cool it off, there's some of the additions. For iron, it's the carbon. The carbon doesn't want to stay in the iron, so it's trying to make its separate phase or different kinds of phases. And when you let that happen in the cooling process, it forms what we call dendrites, or a very, very specific microstructure that's intermixed between soft and hard. Yes?
Are there ever times when you want a brittle metal?
Very rare. The question was, do you want something brittle sometimes? One example that's been brought around to me a number of times is gray cast iron that's used for machinery. And what happens there is, when you have these soft and hard zones, you can have kind of micro voids in it, and it's damping. So it's absorbing some of the vibration as a result of this complex microstructure, but it's very rare. It's a lot easier to think of the opposite process where, if we go back to that fitting, we want to do it by casting, but we also want to be tough. And there are processes. The purpose of this slide is through thermomechanical treatment and a special sort of combination of chemistry, you can, instead of having these little lamella in the microstructure, you can get the hard parts being nodules in the microstructure, and that's how you get more ductility. So these type, the big water pipes, these, for example, a lot of time are made of ductile iron. Now, it is cast iron that was just made in a way that this brittle zone is in nodular form and is not going to impede the ductility. It's a very high volume. We have a lot of big diameter water pipes at a lot of places. A lot of them are reinforced concrete because of cost, and Professor Eager is going to go through that. But when you are in, let's say, a water treatment facility and you got all these lines, making them out of cast iron is a standard way because it's very ductile. There's no risk of brittleness at this point, and you can have all these complex shapes with huge flanges to put the bolts and all that. So it's just a practical way of doing it. If you were trying to take plates and machine all this and weld the pieces together, it'd be just very, very expensive. It's not that it can't be done, but it's just very, very expensive. There's a way that you make these, it's a centrifugal casting process. So you have your mold spinning and you come with the liquid, you put it in, and then eventually it solidifies. And you have to go to some heat treatment to get this nodular microstructure, and then you're good to go. But you got a big piece all made at once. So that's the big advantage. Okay, so how does casting work? If it fulfills the need for strength and ductility and corrosion resistance, it's typically a low-cost alternative. You have to be able to make a lot of them, typically to cover all the expenses to set it up. It's involved almost always in making metals, from refining the ore to coming up with a product. Eventually you're like, okay, this is the chemistry I want. I'm going to solidify it and then try to do something with it. So what happens when you cast, it's the end product, whereas in other situations you make these big bullets, and we'll see some example of them, and then you deform it until they're just really homogeneous and really tough, good quality material, and then you make plates or bars, tubes, extrusions, different products with them. So most of the time, if it's a small quantity, you end up with raw product. They were cast, but when you look at them under the microscope, you don't see any of these special features that you would have with a casting. Okay. I will be talking about polymers casting as well, because it's too easy for me to go on metals, and just making the complementary way, I think, makes analogies for you guys. Okay, these knuckles, they were making them by the 100 per year first and then 1,000 per year. It's a sand cast. It's the easiest process, if you will, to make castings in terms of the molding. It doesn't involve making a metal mold that is very, very expensive to machine out of a hard material. The place they use them, if you're interested, is where you connect to the wheel. So over here, you have these A-arms or control arms, and then you have this piece laying out that goes between the different arms, and the suspension goes like this. So the purpose of this is really to take the moment from the wheel and transfer it to the A-arms. And very interesting, and this is something, a lot of you guys are mechanical engineers, so it's twice as wide here than on top. And what happens is you have the A-arms, you have the ground, and this is for skidding that you get the most load here. So when you skid, yeah, it's literally just a 3-point force equilibrium. So you have the ground. Right in the middle is where you have double the load as opposed to the other extremity. It's just a simple bending equation. It almost works exactly. And it makes for a very, very simple calculation. So it does require strength. But just because they don't want this to start twisting and everything, it doesn't need a whole lot of toughness. This unit is on wheels. You have to keep that in mind. So there's always a certain energy absorption, and it's only if you hit a wall or you have a rollover that you start breaking these. And that is what was happening in this series of testing that I was involved with, where somebody will say, I was driving and then the wheel came off. Okay, is that really possible? So then you start going through the entire analysis. No, it's just the way it is, and it's unfortunate, but for engineers, it is an opportunity to try to go back and see, is there really a problem here? And in this case, there wasn't. But if you have the side load hitting the wheel itself, the rim, and in a rollover situation, it turns out in some cases, you could break this knuckle. It doesn't have anything to do with the initiation of the event, but it is, I guess, another example of failure analysis. When you're done, in this case, I know the manufacturer still decided to use something else because they didn't want to deal with all this back and forth about it. Okay, so the alternative to making this complex shape all at once is to have these bars that you manufacture and assemble together, bolt together, and all that. And it can get very, very complex. You can make a lot of very complex shape, but it typically starts with a lot of steel. Probably none of you have been to these mills, but it is very impressive. It's really, really hot. A steel mill or a rolling mill, you need the special safety hat, the clothes and all that. If you're working close, these are very, very special gloves. It's, at this point, it's around 1400 degrees centigrade there. And what it is you started vertical into this cavity, so I have a schematic of it. So you have your liquid that gets into a mold vertically, because otherwise you can't do it as a continuous process. And this mold gets cooled, and so you start to solidify on the outside and then get to the center. So what happens on a big part like this, an ingot, is you see this chill zone. You have a very different microstructure on the surface, and as you get to the center, it goes through different stages. Essentially, your cooling rate's going down. And then you also have an effect where a lot of the alloying addition that you put in stays with the liquid. It's thermodynamic. They don't really like the solid as much. There's not as much room for them. So what we have what we call chemical segregation. It has a lot of implication, because when you're done with casting, this is what it looks like. So there will be a very, very few applications where that's okay. But in general, that really is the driver. It's the reason why you go through all this rolling to avoid having all that segregation. And so it's not so much the fact that you can't go to the hardware store and get you a bar that we don't use casting this much. Otherwise we would have a casting house. A little bit like right now at MIT, people are developing these metal printers, and it's a challenge. And you can see a little bit some of the reason why it could be a challenge to make a reliable part just by casting it. But we by understanding everything, it can be overcome. But traditionally, the reason why we use raw product is we need a certain toughness and homogeneity in the material, and a traditional casting process doesn't give it to you. So I'm really talking a lot today. Anything so far? Anything that not clear, boring? Yes?
I have a question about this. How big are those?
It depends. So if you're going to make, let's say, suspension components, like the big torsional springs or just these leaf springs, you could start by about 10 inch by 10 inches in this continuous casting process, and then take it down to that bar size. If you're looking at making a big plate, a lot of times it's a broom and it's bigger to begin with. And it's a very, very good question, because one thing I realized I put it on here is some of the development, especially for aluminum, if you're going to make aluminum foil, you don't really want to start with something that's this big. So they developed strip caster process. So here you have two wheels spinning, so you can start with something that is thinner, a lot thinner. And it's just part of this, continuous improvement. It's still the same process, but it does allow you to vary. I think you can start with less than an inch on the aluminum as the most typical way of doing it, as opposed to being this big. But doing it big is still common for big pipes and large beams.
But it's got to take forever to cool down, right?
About the cooling of the steel, a lot of times it's almost desired. So if you have a mill that's set up to cast, sometimes it will feed the hot product to the rolling mill that's going to do the deformation processing, break that down. And we'll go through that. We're kind of we're almost skipping a step, but essentially you don't necessarily want it to cool quickly, is what I'm saying.
You want it to cool quickly so you can get more done.
Yes, okay, so about getting stuff done, because it's continuously casting, they get piled up. So there's a cooling bed that stuff just get lined up there and then picked up. So these are huge facilities where you do this. A lot of times people will worry more about the time where it's in the oven, for example, because that's the expensive piece of equipment, as opposed to sitting out there where they just put more room if they need more room. Yes. Very good question. Thank you. Yes?
With the parts that you have coming through a vent, does that give you asymmetry in microstructure with one part?
Very good question. So at that point, and we can go back to this schematic, it's just so hot that mechanically there's not a whole lot going on. And in terms of diffusion, the chemical diffusion doesn't really care the orientation. It's not affected by gravity. So there's not really an effect there. There are a couple of really important things that from just the discussion we had about the time to cool and how hot it stays is these are just in air. So you have carbon in your steel and it's going to oxidize. So you lose some of your carbon on the surface just through that process. And that is one reason why keeping it really hot, if you can avoid it, you do. Because otherwise there's a certain amount. It could be up to 1% of thickness on the surface that your steel doesn't have all the alloying element it should have. And some of that will stay permanently. So when I was talking about oil and gas pipelines, it's a major issue. When we come with our equipment, we have to remove enough material to remove that decarbonization layer. This all comes in, as you can see, between the startup, the lecturing, and the consulting.
Why don't they do it in a vacuum?
Okay, about casting in a vacuum, it is done for certain special applications. Let's say you're going to cast titanium. You'll do that in a vacuum a lot of times. There's some aluminum processes that require it, but the main reason for trying to avoid it when you can is cost. Before you do it on a vacuum, a lot of times you will have a shielding gas atmosphere. So you put it in the nitrogen or argon, and that is less expensive. It's just putting on the pressure. And I'll add one thing with respect to vacuum is sometimes you will lose some of the alloying element, the low weight alloying element that goes into the vacuum. So there's some pitfalls, but you don't get oxidation. So you have something that helps you. Okay, so we talked about really why we're doing castings. Now we're going to go a little deeper into the thermodynamic. And don't get too worried about it. I'll draw, I guess, well, I should probably just use this so we don't have to spend as much time. So this is the iron-carbon phase diagram. Iron is here, carbon is there, but it's only stopped at 7% carbon. Traditionally, if you talk to a metallurgist, that would be probably your grandparents, they'll say that in the entire 3 or 4 years undergrad learning metallurgy, that was the most important thing. That's the thing that they can summarize their thesis on. Now, we're in a different world, so I'm not going to hold you to remember all of this, but the main significance, if you understand it a little bit, and we'll try to understand it a little bit more together, is it puts things in perspective. What's so different between iron, steel, cast iron? They all seem boring. I mean, but they are very, very important. We use a lot of this. Professor Eager is going to go through this. This is a very, very high volume business when you pass the stage of concrete, aggregate, and sand. When you're starting to talk about metals, this is where you start. Okay, so pure iron is soft. Very soft. And when you get to a point of mixing it with carbon, a lot of things happen. So at high temperature, you'll see the word liquid there. They like each other. The carbon just goes around and it just looks like water. When you start cooling down, well, the melting point of carbon is a lot higher than iron. The two of them together, you can keep them liquid to a lower temperature. Well, that's awesome, because the first thing you want to do if you're going to cast something is heat up as little as you possibly can. This is really, really hot. So why, very long ago, 16, 17, 1800, cast iron was just so dominating how you'll make cooking pans, how you make stoves, is guess what? They couldn't melt it without killing themselves. So the combination of adding the carbon to the iron takes you a melting point. If you go all the way to the left, it's 1550 or so, and then it takes it down to below 1200. It looks like nothing, but when you talk about this kind of temperature, the problem always is, in what are you going to put it in? If you try to heat up, and a lot of time it's refractory, so things that crack, that don't like thermal shocks, it's very hard. And that was the biggest challenge in our work with Tiffany, is where do you put the platinum to make the thing? It's just, everything is just very, very difficult because we're dealing with high temperatures. So being able to lower the temperature is the primary reason we use cast iron for casting. So over the past 20 years, you can have more and more of the cast steel. And if we go back to buildings, there'll be some junction points, very complex brackets that have to help in case of seismic event, just make the frame ductile. And some of those can be manufactured today by casting steel. You don't get essentially this brittle face that we talked about with the cast iron, but these are processes that operate at much higher temperatures, so it is a lot more expensive. You can do anything you want. It's just a matter of, ultimately the cost associated with it. So the pure iron is not used a lot. When we talk about steel, we're not in this high carbon zone. So the high carbon zone, we just killed it. Cast iron, it's inexpensive, it's great to do. If you're willing to spend a little bit more money and you got all these manufacturing processes to do this continuous casting, it's great because then you have some benefit of the carbon in strengthening. That's really is the main thing that it does. It increases your yield strength, it increases your toughness, so you can reduce the weight of anything you build. And there's been growing improvement even the past 20, 30 years, and putting a little bit of this, putting a little bit of that. So the car frame is much lighter than it used to be because of these special development in adding more than just carbon, a little bit of this, a little bit of that, and then you get a good combination of strain and ductility. We'll talk about some of that in heat treatment, but what I want you to keep in mind is we have these two zones. One here goes from the liquid to the solid, and that's about it. You go through these processes to try to not have a big lamellar structure that's brittle. If you want the real high strength and a wrought product, you will cast the steel and then go through a lot of thermomechanical treatment. So maybe the last part, if you'll bear with me on the phase diagram, is we have this solid face here that's called the austenite. That's the red steel. And there is an tectoid transformation from one solid to two other solids here. That is really where a lot of the action goes on. So when we talked in the first class about, I said you're going to quench it and then you have to temper it. So that's really was all associated with how you make that transformation from the red steel to the other one. If you quench, you avoid the decomposition into the iron and the carbon-rich phase. But there is a transformation in this particular case with steel. It is so unstable that it becomes a tetragonal structure. It goes from a cubic to a tetragonal as it's trying to accommodate that carbon in there. So if you start, and we didn't bring these, but you just start like this. It's a cube with face-centered cubic to begin with. So you have one here, you have one on top. You have one right here, one in the back, right there, and one at the bottom. Okay, so what happens is carbon can go freely in there in these high temperature range when the steel is hot. Then you get to this point where the steel is no longer stable in this phase. It's trying to become a body-centered cubic, but there's not enough room for the carbon in the body-centered cubic, so it stretches in one direction to accommodate the carbon in that location. And we call it a military transformation. It happens really, really fast, and that's the martensite. And because it's tetragonal, it's not ductile. So that may be a way you remember. Guys, that quenching steel can cause you some trouble. So you heat it back up, and then it goes back to these equilibrium phases. Depending on temperature, you get it real good, or you get it, not so good. All right, aluminum, maybe I should have started there because it's a lot easier. This is a phase diagram of aluminum and silicon. Same story where the silicon is much higher melting point. The two of them together reduce the melting point. This may not look significant to you, but again, traditionally and even today, adding silicon to aluminum is the first thing you do when you know you're going to be casting it. And there's more than one reason. Let's think about this. So when you go here to this eutectic point where you're going to combine and start making two faces when you solidify, if you know you're making two faces, it's going to sort of make a two-phase structure right off the bat as opposed to making these big, huge crystals that can take over all the way like from one side of the window to the other. So it breaks down, your cast structure is finer than it would have been if it was a pure alloy. And if you're not going, just like this one, if you're not going to deform it after the fact, that's what you want. You want something that right off the bat after casting, it's not so intricate, like big fingers interlaced that are just waiting to spread apart. So if it's already blended in a fine structure, that's how we use a lot of the castings. So the majority of the castings are alloys for that reason. So what happens? Talked a little bit about this. This essentially is probably the most complex, definitely the most complex we're going to go today. It explains a little bit how you arrive to a phase diagram. So if we go to the lower portion here, that's the energy of each phase as a function of composition. We got different curves. So this is one solid that is rich in ACE. Let's say it's aluminum. Then you have the liquid, and then you have another solid. So what happens is it explains a little bit why you combine. If you have this option, you have these three things you can make. If you just make one, if you have this composition, you just make this one, it's going to be very high energy. If you make this one, also high energy. So the way you minimize your energy is by having these two faces. So that's how thermodynamically it's favorable to separate. And these separation points, so when you draw those straight tangent lines, is the lowest energy. So you have a little bit of this and you have a little bit of that, so your average energy is right here as opposed to being here or way, 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 way up there. So that's just how it works. What does it mean? For us, it means typically that anything that is pure, let's say I'm here, is not going to want to be, all in the liquid. There's so much energy, anything that's solidifying. So this is a solid and this is a liquid. So what solidifies, let's say, I'm going to simplify this. This is our average composition. And then I want to minimize the energy here. So what am I going to do? I'm going to make the solid with a small amount of addition in it. And then the liquid is going to become more and more rich in that same addition. That's really is the fundamental reason why we have this chemical segregation. Everything that starts to solidify with metals is going to have less additions in it than the last bit to solidify. So what happens is it leads to these dendrites. So let's try to think about this. If I have a perturbation when I start to solidify, so let's say it's perfectly straight, and then I'm going to go through a little bit of a perturbation. Okay, so what happens here is this is my solid, and this is the same, but with a perturbation. This is low in B, so B is just very low, B is very low. But what it means is you keep pushing that alloying element into the liquid. So in these zones here, you just have more of B. That's not what you want. I know you want an A, but for here, we'll do a B+. So you're not going to continue to grow at this location. What happens is when you have this protrusion, it's accessing, let's say I'm going to plot it this way. Your concentration of B, this is B as a function of distance. It's very low in the liquid, then it goes high, and then it goes back to this tangent equilibrium here in concentration. So you try to, by any way you could, to bypass your solidification front, and that's how you end up with dendrites. You just try to peek right through this buildup of alloying element in front of you. There are ways by cooling rates that you can try to minimize that. But it's not easy. So a lot of times casting faster helps you avoid some of these issues. It's just going to go. So you make more dendrites, they're all smaller, and life is better than just... I keep using the example of a crystal on the window, but I think it's really valid. If it's frost, it happens really quick, it's going to be all very fine. If it's just started to cool really quickly, then it's different. All right, maybe this is where we will have to stop with this whole casting business for today, but talked a little bit enough about making big pieces, so we're going to take the opposite end and making these rings. It's called an investment casting. What happens here is, well, there's so many casting processes. That's what I should say first. The one that is the opposite of trying to take something big and lowering it down is you make a piece of wax of any shape you'd like, and you set it up as a tree shape. And maybe I have that. I do. Okay. You set it up in a tree shape. So what happens here is you dump this in a slurry of what you want to use to make your shell, to make your mold. It's a low temperature process. It's essentially by stages. You keep adding and adding, and you build up this shell around your wax. Then you eat it all up. The wax gets out. And you have this very intricate mold that you can use to cast anything you'd like as many pieces at a time. So for jewelry, it's perfect. You get to be so refined, and it doesn't take a lot of energy to make the shape you want out of wax. Then you get your mold done, and you pour the metal typically from up above. It's going to come here and go back up into it. That's a very, very typical process, and that's what we were sort of looking at here, where you have a mold and then you fill it in from the bottom up, and you hope for as little porosity as you can, and that depends if you're going to be in a vacuum, if you have a shielding gas, what metal you're casting, at which temperature. So this is, you know, the small size. Then the sand cast like this one here is a little bit simpler, where what we have in bluish is the part that you're trying to make. So you make the impression in the sand with that part, and then you get that sand to consolidate. You have this treatment to make it a solid mold. You take your part out, and then you pour the liquid into that mold after you close it. So you typically have halves. I didn't say that when you make those sand casting processes. So you only need to make one pattern in this case, and you can keep reusing it, but each time you do need to make a mold. So it can be, you can reuse some of these. I'm sorry, you can reuse them. It just depends exactly what you're trying to do. The most common sort of high volume process involves essentially a metal, metallic, especially if it's aluminum and you're trying to make aluminum wheels. You can use metallic molds and have this high cooling rate that gets your microstructure really, really fine. And that's probably where we're going to stop, just to show how fast these things can go. I think it goes through a few cycles. So they close the mold. It's going to pour the liquid in from this big tank, and then after a couple minutes, reopen, and you have your part made. That's it. There are a couple of things that happens is you do have to do some cooling and stuff. Like, see here, they're just cleaning the mold to go to the next one. But it's all in air, and it happens fairly fast. And again, it's not just a question of efficiency that they have these metal molds, it's to be able to cool fast and have that fine microstructure. So it's very typical die casting process used to make, not this one, but when you have a much larger quantity. Getting this machine set up with the right cooling rate for everything you make is a big project. But it's useful. It allows you to literally almost print parts at that point. So I'll take any other question you have, because I'm going to have a few more things to cover next time. Yes?
For investment molding, so you have wax and you dip the wax into the metal?
No, you dip the wax just in a cold slurry of kind of like what's going to become your ceramic shell. So you have the wax, you build a ceramic shell around it, and then when you heat it up, you consolidate that ceramic, so it becomes a really hard mold, and then your wax just falls through it.
Oh, I see.
Yeah, and then you can. Yep. You get the metal, you set it up, and then you fill the metal into that shell.
Oh, okay.
Yeah, typically from the underside.
Okay.
Yes.
I know 3D printing is like advancing. Do you think it'll ever replace casting?
For some applications, for small parts, I do. I'll bring, next time I'll bring you something that was laser sintered. When it's small, you can make a couple inches now. It's not that expensive. You can make so even today, if you're looking for something really, really intricate, you can consider it. Big pipes, you know, why would we try? Because it's just a question of cost. The same way that we use concrete and asphalt to make roads, it's just the scale that makes a lot of things impossible. So what I would say from reviewing technology and stuff is typically something comes and replaces a little bit of a niche application as opposed to overtaking the whole world. There will be things that overcome, but a lot of times it just takes its own space. A very good question. Anybody else?
So with sand casting,
Yes.
you get a lot of variability when because you're remaking the mold every time on a certain piece.
Yeah, okay, so again, you can reuse, yes, it is a relatively low quality product. There will be variability, there may be some coarser particle. If you need, and it's hard to inspect too, just if you look at the surface finish, if you try to do a non-destructive test here, Brian can speak to that, but it's not as easy that if it's been machined. So the main reason is cost, and when you don't need that precision. You have to be willing to accept there's going to be some inclusions. And I have a lot of examples of that. It does happen. You always have something in there. And if it's failed over time by fatigue, typically that's where it's going to break. So you get to see them if you're willing to wait long enough. Yes?
For this video example, how do they make sure that the part stays on one side of the die, not the other?
Well, I really don't know. I haven't really looked carefully exactly what the sizes are. They will have a lot of time, it will stick on one side, and they have an extractor that's pushing it. And maybe this one we see those extractors. So the side that's more intricate typically will dictate where the stuff stays and also where you supply it. You supply it from one side, so you got to break something there because it all got solidified. So by default, I think there's just going to be one side that's going to stay in because you have that supply coming in of the liquid. It's very intricate. One thing you want to make sure is that it's not cooling too fast so you don't fill your bowl. There's really a compromise. And there's a variation of this where what your feedstock is a combination of liquid and solid, so you don't have as much shrinkage, and you make better parts if you're willing to go through that process of having a feedstock that already contains solids. You guys have a lot of good questions. Thank you so much.